everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken, University of Albany, and Seth's brother Joel Chaiken. We're here to hopefully show you how to approach SAT math questions. And today is Throwback Thursday, which means after this we will go and look at two questions from a test from about 20 years ago when the tests had a whole different feel to them. So here we go. Let me make sure I'm in small mode. We have this thing. What's the least possible value of that? Pattern. They love this question, and it's interesting, right? You want to go 2p, 3p minus 2 is greater than or equal to 1. Add 4 to this side, add 4 to this side. 3p plus 2 is greater than or equal to 5. Done. Right?
Okay.
Done. Now, the other way to do it,
okay, great. What this tells you...
Wait. Let me say one quick thing. You can do it by solving for p. You can do this by solving for p. Oh, God, it froze. You can do this by solving that inequality for p and then throwing p into here and getting 5. But that is a real slow way to do it.
That's terrible.
Yeah. But a lot of people, but if you don't see the pattern, you don't really have a choice.
Yeah, okay. Well, I identify this is an even more striking feature of the pattern. Let me write it out.
Sure.
What you're given is 3p minus 2. And then you're wondering about 3p plus 2.
Right.
Well, you get from here to here by adding 4.
Right.
And then you're being told that this is okay, never mind. You're being told that this thing is greater than or equal to 1. So the least possible value of this thing is 1. And the thing below it is just 4 more.
Right.
1 plus 4 is 5.
Right.
Which is what you got.
Right. So when you see problems like this, and these problems come up a lot, and I'm sure by studying for the SAT you will see this type of problem come up again and again and again and again and again. This is how you do it. This is how you do it. You will lose a lot of time solving for p here, and then throwing the p in to the thing. Just like I lose a lot of time getting frustrated that my computer board has just frozen.
Yeah.
Okay.
Well, we solve for p. First of all, you can't solve this for p. Because there are many p's that satisfy it.
Right. It would have to be p is greater than something.
And they so the logically correct but wasteful strategy is to realize that the maximum value attained by 3p plus 2 is attained for the same p. Well, it's the maximum value that's attained for the other one.
Right.
And then find the maximum value for p that's attained, and then you plug it into here.
I guess we can do it.
Yeah,
even
so
though 3p is greater than 3. Oh, p is greater than equal to 1. What 3 plus 3 times 1 plus 2 was 5. It's not that much longer.
It isn't.
It isn't that much longer. It isn't that much longer to solve for p and then throw
p is strictly greater than 1.
P is greater than 1, and then
and therefore 3p plus 2 is greater than was it? P is greater than 1. 3p is greater than 3. Greater than or equal is greater than or equal to 3.
Right.
Right.
Yeah.
And then 3p plus 2 is greater than or equal to 2.
No, 5.
So it could be 3p plus 2 is greater than or equal to 5.
Yeah. So
and so the smallest it could be is 5.
Right. Oh, yes. Yeah, so,
right.
actually not solving for P, but
Yeah.
dealing with it directly isn't that much longer. But
No.
but sometimes it is. And that's why this is a good way to do it for future problems. I guess we're done.
Yeah. You don't have to deal with P with the oneness of P.
Yeah. Are we done?
Yeah.
Done?
Yeah.
Done. Okay,
yeah,
so it's
Throwback
so. Yeah, Thursday.
Okay.
If you don't want to stick around for Throwback Thursday.
Throwback Thursday.
Then either like us, dislike us, give us comments so that we get some feedback so we know how to make this better for you.
Yeah.
And now we will go to Throwback Thursday. We will go back to
Throwback
20
Thursday.
years. So we have
years old.
Hopefully this thing's not going to freeze.
Yeah.
The Cypher thing has a very nice feature where we can just zoom. Oh God, come on, don't freeze on us. We go back up 20 years. There's a big circle here somewhere. Here's the big circle. TT stands for Throwback Thursday, as everyone can see. And we will continue sort of where we were last week. Where these are the problems where you have to choose column A. Say A if column A is bigger. You say B if column B is bigger. And C is if they're the same. And D is cannot be determined.
Well, more accurately, A, B, C, or D, if the quantities in the box under column A is greater than the quantity in the box in column B.
It's just there to make sure it's precise.
It's not the columns that are comparable; it's the entries in one row of the table.
That's
which
right.
Are two boxes.
And I'm an engineer.
Yeah.
Okay. Here we go. Oh God, I don't like this one. You may have to help on this. We may have X minus Y is equal to 7. X minus Z is less than 7. Which is bigger, Y or Z? A or B? Cannot the same or cannot be determined.
Okay. Well, I want a relationship. I want to figure out a number comparison relationship between Y and Z, and now I see immediately that there are X's in these two linear left-hand sides. Eliminate. Subtract the top inequality from the bottom. I'll eliminate X. Now we have to do some careful algebra. What you write here is minus Z minus a minus Y minus Z minus a minus Y, which is a plus Y, is equal to the relationship becomes, now be careful, I am subtracting the same thing from two sides of an inequality, and that keeps the kind of inequality. Let's see, so the left-hand side is minus Z plus Y. The relationship symbol is less than, and the right-hand side is 7 minus 7, which is 0. So this tells us that, minus Z plus Y is less than 0. Now add Z to both sides, and I get Y is less than Z. And then we're asking, the Y is in the box of column A, and the Z is in the other box. And the question is, which one is less or smaller? Or can you tell? It can't tell. And so we see that the Y is less than Z. So we could translate it here. And now we have to carefully pick which of the four choices to put in the answer, A, B, C, or D. And after, do you remember that? It's a good idea to look up. I think A means the entry in column A is bigger than column B, right?
Right.
B is the entry in column A is smaller than the entry in column B, right?
Right.
Well, here, entry, this is a less than sign, so this is the smaller. And this is the bigger.
Right.
And so the answer is that.
Okay. Seth, I don't know about anyone else, but I sort of got lost here. So let me also try it. But that's because you have an equality sign, x equals 7 minus y. Seth, get rid of all that. I need space.
Eliminate it. Eliminate
okay,
is
Seth,
the way to go.
Seth, please get rid of this.
Okay? Eliminate.
Eliminate what you wrote, because I need
X
Seth,
is
Seth,
a complaint.
Seth, you already did it. Let me try.
No, I don't. I still have the E and the L.
No. You did the problem. Let me now try it, okay?
Okay.
Okay. But I'm going to do it a little bit slower, I think. X equals 7 plus y. See, I made a mistake, so let me fix that. The thing froze. Okay, right? X equals 7 plus y. So now I'm going to throw my x into this. So 7 plus y minus z is less than 7. Subtract 7 on both sides. Y minus z is less than 0. Y is less than z.
Okay.
That's
well, you did the same thing. You eliminated x.
Yeah, but I don't know what you did here. I don't know what you did.
I eliminated x by combining the two inequalities,
but they're not
by adding the left side of one to the minus. I eliminated I processed the two inequalities by subtracting the left side of one from the left side of the other, and the right side of one from the right side of the other.
Okay, now, Seth, you just said to me, you have to be careful how you do the columns. Right?
I was careful.
I know, Seth.
I was careful to subtract the top one.
Seth, let me finish
I'm explaining.
talking.
I was very careful to subtract the one that had the equal sign and not subtract the one that had the inequality sign.
So listen to my point.
Yeah, care.
Okay, but you just said something that wasn't true. You said that you're combining the two inequalities.
Yeah.
No, they were not.
An equation is a relation. It's a side, equation, inequality.
That's not what
they are linear equation or inequality relationships.
Seth, that's not what you said. You said that you're adding and combining two inequalities.
Yeah.
This is not an inequality. This is an equation.
An equality, yeah.
Okay, now
you
said, but no. Hey, don't hold the different standards here. Don't hold the different standards, right?
Yeah,
I'm a little loose with what I said. We have to hold you to the same standard.
Oh, no.
Those are not both inequalities. One is an equation. One is an inequality.
Yeah,
so
right.
I didn't know you can do that. Wait.
I'm sorry.
Oh, it's okay, Seth. It's fine. You mean you? I didn't know that. You can do this. I never knew that. You can go like this, and you could go like this, and subtract the two. You can do that.
If the result of the subtracting, if when you do the subtracting, you change the direction.
Oh, forget it.
Yeah. Because subtracting means you multiply both sides by -1 and add. And when you multiply an inequality by -1 to preserve the truth, you have to reverse the direction.
Oh, so in other words, you say that it's safer to do -x plus y is equal to -7, and then add x minus z less than 7. You add these, and then you get
Yes.
y minus z is. But what? See, what do you? I've never done this before. I've never added two relations. One is an equality, and one is an inequality. Never did that in my life before.
Well, I have.
Well, but how do you know this is true? What's the justification?
The
What's
again
justification for doing that?
the reason it's true
Yeah.
is that is that uh is that well let's see, if you add the same thing to both sides of an inequality, the inequality is preserved.
Okay, that's a good justification.
Okay.
That's a good
If you
justification.
have, say, let's see, why would it be? Well,
No, but that's a
say, suppose you have x is less than y and z is less than w.
No, Seth, what you just said is enough justification. You don't have to.
Yeah, that's the justification for this.
Yeah.
But if you have x is less than y and z is less than w, you could do x. It is you can you can conclude that x plus z is less than y plus w.
Right. Okay. Right. I see.
Yeah.
I see. That's even a stronger thing. All right. So if x equals y, then x, then z plus x.
And the only thing is, if you have x less than y and z is greater than w, you can't. No, but you could do is subtract this one.
Right.
When you multiply this one by -1, you get minus z is less than minus w.
Right.
And then you could take these two and add them.
Got it.
And get x minus z is less than y minus w. Yeah.
Okay. So then that's good. So in other words, you really got to be careful. Wow, that's dangerous. If you do elimination and you're not careful about that, you can get a problem.
Yeah.
That's why I took the safer approach, because I took the guaranteed route here. Except this thing froze again. I took the guaranteed route, and I used substitution rather than elimination. Elimination's faster. But in this case, I like substitution because I knew this to be true. Okay? I knew this to be true. And then I substituted in. And then I had more confidence in what I was doing.
Yeah.
Okay. Great. Okay.
Yeah. Well, the reason I know about this approach is that I studied it in my studies of inequalities,
right?
And it's there's a bunch of rules that were worked out for solving linear inequalities by Fourier. And all of the rules for of this sort were codified and put in writing for dealing with large systems of linear inequalities. And then a method was developed to apply the rules systematically to simplify, to do simplifications of systems of inequalities, and to tell whether or not they can be satisfied. And the method was developed by Joseph Fourier, whose name also is given to Fourier series.
Right.
It's a method for solving linear inequalities. It is an alternative to what's called today linear programming.
Got it. Okay.
And it's a systematic manipulation of the inequalities by this kind of thing. You multiply both sides by either a positive number or a negative number, and switch the direction appropriately and add them, and that's yeah. So this is not something I dreamed of. It's not something I thought of doing right away. It's something I learned a few decades ago.
But if you're coming in without a PhD in math that you did, substitute, using some method of
Yeah.
substitution for getting rid of the x and throwing the x in here is a reasonable.
Yeah. Oh,
reasonable
yeah. Yeah,
approach.
for sure.
It's a
I see.
reasonable
Yeah,
approach.
certainly. And so getting rid of the strategy, how do you approach SAT questions? Here's a strategy for approaching SAT questions.
Good. That's what we're here.
The expressions in the boxes do not involve X.
Right.
But the data does involve X.
Right.
Wouldn't it be great if you could get rid of the X?
Right.
Well, that's what Joel did.
Yeah.
Yeah,
Okay.
to solve for X in one equation, and
Right.
then substitute that solution into the other equation. What that does is replace two equations with an X and other variables with only one equation where the X is gone.
Right.
That is called eliminating X.
Right. Exactly. That's the key.
And so what you have left, there are two other variables, Y and Z, in this problem. Eliminating X gives you one equation instead of two, with Y and Z instead of X, Y, and Z.
Right. And that's the goal.
Now, elimination is I guess you first encounter when you work with solving not inequalities or combinations of inequalities and equations, but with solving equations alone.
Right. Of course. Yeah. That's known as the two equation to unknown problem.
Yeah. So this case, it's really well, again, they're not equations, but what you might have is two equations in three unknowns.
Yeah, let's not go there.
Here you have a system of linear relationships. One is an equation and one is an inequality. We have two.
Right.
Two relations and three unknowns. We eliminated one unknown, and we got one relation between two unknowns.
Right, and that's why we can't actually say an actual number for what X, for what Y and Z are. We can't say that Y is 3, and we can't say Z is 7.
No.
We only know the relationship between the two.
Yeah.
Okay, should we move on to one more today?
One more, yeah, sure.
Okay,
Let's do one
it's
more.
Located here. It's little neighbor. This
neighbor.
one. Oh, looks like we're into geometry now.
Oh.
H is greater than 1. Oh, how about if we draw a equilateral triangle? Okay, that would help. Equilateral triangle with height H. Equilateral triangle with side length H. Which perimeter is better? 3H
bigger.
Or 3X?
Okay.
Aha. Let me go like this, so maybe a little drop per permanent out, drop per perpendicular.
No. Isn't X bigger than H?
Yeah, X is bigger because it's the hypotenuse, right? Yeah. The hypotenuse of a right triangle, X is always bigger than H.
Even
right?
worse.
Yeah.
Even worse. H is the exact distance between the tippy top and the middle of the bottom. X is a distance you use to go around. Perpendicular. Yeah, the perpendicular. H is the length of the perpendicular from the tippy top to the base. The shortest distance, so there are these 2 points. The shortest distance between these 2 points is a straight line.
Right.
And the shortest distance from the tippy top to the whole line is the perpendicular. X is therefore a longer distance from the tippy top to somewhere else on the line.
Right.
So let's see. So what to be truthful, the reason X is greater than H is that H is the length of the perpendicular to this line, and x is the distance along a non-perpendicular.
Right.
And therefore x is bigger than h. Therefore 3x is bigger than 3h, and therefore 3x is the perimeter. 3h is the perimeter for this, and so it's greater than, and so you pick of, the choices A, B, C, and D. You pick that one.
Right. That's right. So that was wow. So there were different ways to approach this. The hypotenuse is bigger than any side of the triangle, but I like the way Seth did it.
Yeah. So you really this triangle is really, it's more like this shape. More like you draw it to scale, would look like this.
Right. So
this is h. So this is this height. You kind of put it on its side.
Yeah.
Bring it over to here, and the triangle gets smaller. So this triangle's smaller.
So this has an application that could save your life. Yeah. Then it had an application for me. It wasn't as dramatic. Well, it was pretty dramatic about getting to a spot as fast as possible. But let's discuss jaywalking in New York City. I live in New York City.
Yeah.
Seth went to Cooper Union, right? Go for Cooper Union in New York City. So Seth did a lot of jaywalking, right? You did a lot of jaywalking in New York?
Oh, yeah, sure.
Yeah. So this is really important when you jaywalk. If you jaywalk and you are crossing the street here, right, and a car is coming, don't go that way. You don't say you're going to walk in this direction. No. If a car is coming, go directly to the other side and don't stop go, as they say in Monopoly. Because this is the shortest distance, and this could save your life. If a car is coming, don't try to do any of this stuff. No.
Well, what about this?
No.
Walking towards the car is stupid.
Yeah.
What about walking this way?
Well, actually, going back, maybe.
Does this make any sense?
No, you want it. Okay, first of all, what you may actually want to do is get back. Like, if you're just starting out and a car's coming, obviously you come back. We all did that, right? But if once you've committed to going and a car's coming, go absolutely straight, perpendicular to the other side of the street.
Yeah.
Because it is the shortest distance. You're going to get there as fast as possible.
Is it? It depends. Well, let's see. If you jaywalk at a given speed, right? And you're so stupid as not to judge your speed safely, and you end up getting to here the same time the car gets to here. Now, suppose you go the same speed this way. Well, in the time it takes you to get to here, the car is over here, right? You go walk a little further, and the car will go further. So it's hard to tell whether you'll be hit or whether you'll end up being hit late. Well, certainly if you keep going, you'll be hit later than if you went straight.
Oh, I see what you're saying.
But would you be hit at all?
Right.
I think it all depends.
Right.
Certainly, if the car's going this way, and then you jaywalk this way, you're never going to run into the car.
Right.
Right.
Right. Because you're not jaywalking.
And if you go this way, it'll take you a long time, and the car will be well past.
Right. Oh, I see what you're saying. In other words, you're saying there is a possibility that if the car's coming, if you're here, you should actually go that way because you're moving away from the car. But but let's assume the car's moving pretty fast. That would be risky.
Yeah.
Isn't it better just to get as fast out of the way of the car as possible?
Yeah.
So generally, the bottom line is the shortest distance from you to a point is a perpendicular to that point. Just get there as fast as possible.
Yeah. Also, I think that's easiest to judge. It's easiest to judge the your safety and make a judgment about how fast to walk and whether to do it. If your plan is to go perpendicular.
Right,
If you go in an oblique direction, it's harder to figure out and choose a safe strategy.
Right.
Yeah.
Yeah. Okay.
Yeah.
But that's a really important thing to remember. Not only again, on a lot of geometry questions, math questions, the shortest distance between a point and between you and a point and a line is a perpendicular to the line. Just an important thing to know in math and in life.
Yeah.
Okay. So I think this completes Throwback Thursday.
Okay.
Okay. Great, everyone. Have a good week, and hope to see you back tomorrow. Please give us comments on our videos or email us at satmathquestion@gmail.com. And if you encounter some SAT math questions that you want us to go over, please email them to us at SATmathquestionoftheday@gmail.com. Okay, everyone. Bye-bye.
Okay, bye-bye.
Bye.